Hi, my name is Azhal Fayez Nishida. My presentation topic is a solution of traveling salesman problem using deep learning. Here's introduction. Deep learning is a method of extracting rules from large data sets using neural networks. In recent years, it has been developed in various fields such as image processing and natural language processing. On the other hand, traveling salesman problem is a part of combinatorial optimization problem to find the shortest route. This research explores how to find the solution of TSP as an image using deep learning. Here's about traveling salesman problem TSP. Problem definition is that given a collection of cities and the cost of travel between each pair of them, TSP is to find the cheapest way of visiting all of the cities and returning to your starting point. As shown in this figure, several combinations are possible. Of course, there are others, and the shortest one is chosen among them. Contrary to the simple definition of the problem, its solution is complex. The possible combinations of root is n-1 factorial divided by 2, where n is the number of cities. This means that as n increases, the computational costs increase exponentially. It is not realistic to obtain an optimal solution, so it is important to obtain an approximately correct solution by approximate solution method. The TSP has several applications, such as optimizing truck delivery to minimize transportation costs and determining efficient derail paths for circuit board derailing in the printed circuit board PVC manufacturing. Next, I will talk about deep learning. The parameters theta of the neural network are run from a large amount of n-trained data dn. The data is given by the input x and its correct answer y. In training, as shown in the middle equation, minimize train loss R theta by an optimization algorithm using loss function L. Once trained, the next step is inference. In inference, use theta hat obtained by training to input unknown data x and output desired y, if well trained. Next, I will talk about proposed method. Solve TSP as an image using deep learning. As you can see this figure, input is image with dots drawn, and output is image with the shortest path to those points drawn. Solve multi-level binary classification per pixel. So the output solution is an image, and the final goal of this study is to enable visual confirmation of the shortest route. The reason for treating it as an image is that it reduces the increase in computational cost due to the number of cities. As you can see this figure, these two images are same image size, but the number of vertices is different. So computational cost remains the same because of the same data length. One network architecture capable of achieving this task is UNet. UNet consists of an encoder and decoder. Encoder extracts image features using convolutional layers. Decoder restores encoded features to the original size using transposed convolutional layers. Additionally, at each level where the encoder and decoder share the same spatial dimensions, skip connections are applied to concatenate channels, preserving spatial information across layers. Here's about evaluation. The intersection over union, IOU, is used as evaluation matrix. IOU represented by the middle equation takes value ranging from 0 to 1, and the definition of the confusion matrix used in this study is shown in following table. In equation, the denominator represents the total area predicted as black pixels combined with the area that is actually black pixels, while the numerator represents the area where both the prediction and the ground truth are black pixels. In other words, IOU indicates the proportion of the total black pixel area where both the prediction and ground truth matches black, representing pixel level accuracy. Here's about datasets. Datasets using concolv TSP solver to create training data. Optimal solution using concolv for randomly generated vertices. Number of vertices ranges from 10 to 150. The distribution of the number of vertices is uniform, and approximately 87,000 data were generated. Experiments were conducted using generated data. Data sets split into train validation sets in an 8-to-2. 16-layer unit model was used, composed of an 8-layer encoder and an 8-layer decoder. This figure is structure of unit used in the experiment. Here is experiment results. Table summarize the IOU, ROS, and variation data values obtained after training. Using the trained weights, the model's outputs for validation data with vertex counts of 10, 50, 100, and 150 are shown in figure. In figure, it can be observed that for case with 100 and 150 points, there are many partial errors, making it challenging to visually verify the solution due to the complexity of the load. For case with 10 and 50 points, the output is closer to the correct solution, allowing for a rough visual confirmation of the route. Additionally, I plot IOU by number of vertices. As you can see, right figure shows that for a lower number of points, the IOU values vary significantly, with some data points falling below 0.2. This suggests that the model may have overfit to data with a high number of vertices, resulting in poor generalization. This is conclusion. Proposed a method for finding the solution to the traveling salesman problem as an image using deep learning. In the experiment using UNet, the approximate path was confirmed for data with a small number of vertices, but for data with a large number of vertices, it is difficult to confirm the path due to many mistakes. The result was not generalized well due to the large variation of IOU with a small number of vertices, requiring processing that takes the number of vertices into account and training on a large dataset. Here is references. Thank you for listening.